1998, 1998, 99.
1998.
1998, okay. And then he went on to do, he did a lot of very nice work. One of the important thing of Ranjit, which is I see continuing in his research now, is finding new problems. And, he was partly, physical inorganic chemist he was. And so he got a lot of very nice problems. He continued to do that with the postdoc in Professor Mark Marancelli. Then he joined the recent Bose Center. And he has established a group that does both theory and experiment. And he was recently, he's now senior professor after 3-4 promotions. And he is recently elected to the National Academy, Nasi, what we call Allahabad. And so he should have got probably more laurels, but at least we are happy with that he has elected to an academy. So with that, I request Ranjit to give the talk. We always remember students in mind. Okay. All right. Off to you, Ranjit.
Thank you, sir. Thank you, sir, for your nice words. Let me share my files and get set, and then start. Okay, are you getting it? Okay. It's getting shared.
Yeah, you can make it full screen now.
You can make it full screen.
Did you get it? Full screen? Did you get full screen?
Yes.
Yes. I just want to say one thing that, this idea of this, he gave a very nice talk in our conference in Kanpur. So many people said very nice things about this talk. So I thought we should revisit it because that was half an hour. And okay, go ahead, Ranjit.
Okay, sir. With thanks to this platform, SMCB, let me begin. And this is essentially a talk, more of a discussion on sharing results and exchanging views. So with that philosophy in mind, I will share our results and initial studies. Many of them are unpublished on azeotropes. We are in the beginning of construction of a road for exploring physical chemistry of azeotropes with a focus on building a cogent description of structure and dynamics. And at this stage, we'll have some results as we are at the very early stage. And these systems are important because you can see there are some important applications. Your everyday mosquito repellents is one of the most frequently interacted examples of the eutectic system, azeotrope. And of course, it has use in art restoration media, anesthesia agents, and also inflammable cleaning fluids. And while building up a description for the physical chemistry of azeotropes, we took the help of both experiments and simulations. The experiments are essentially spectroscopic, steady-state absorption, UV absorption, fluorescence, time-dependent fluorescence measurements, and occasionally dielectric relaxation. And in simulations, it is essentially following the transport coefficients as a function of solvent composition, as well as temperature, and also simulating the dielectric relaxation, time constants, and other properties, just to find out what exactly is happening at the microscopic level, which is coming up in experiments. And this has a financial aspect as well, since you cannot distill, for example, ethanol water beyond its azeotropic composition. Any more purity you cannot bring in, or you cannot distill further ethanol beyond 96%. You can see that you need to pay more if you want a little bit extra pure beyond 95%. For example, ethanol 95% pure is something like $2.80 per liter, but it costs 3 times more if you go just 1% extra pure, 96%. And this happens, this is particular composition, it's 95.58% of ethanol with 4.58% of water. And this azeotropic composition that is, and the temperature is 351 Kelvin. This azeotropic composition and temperature together azeotropic condition is unique called an azeotropic pair, and it becomes different as you go on for different azeotropes. And for ethanol water azeotropes, this 4.5% of water corresponds to 0.1, approximately 0.1 mole fraction of water. So this thing, definitely the formation of azeotrope has something to do with non-ideality of the solution mixture. And for this non-ideality, we have Raoult's law, which expresses solution properties, could be expressed in terms of mole fraction weighted average of the properties, and which is the straight line. But then in reality, chemical systems, mixtures, we have deviations, and these deviations could be on either way of the Raoult's law. It could be more, it could be less. And when the deviation is positive, and out of that, those systems, if the azeotrope forms, are called positive azeotrope. And when the deviation is negative for those systems, if there are azeotropic pairs, those azeotropes are called negative azeotropes. And when we talk about non-ideality and of binary mixtures, particularly for alcohol water systems, we need to actually specify this azeotropic composition where we are in comparison to the well-studied anomalous behavior and non-ideality of binary aqueous mixtures of alcohols. Let's just have a very brief survey on that. And as I said, these anomalous properties have been studied for alcohol water systems for a very, very long time. And these are just a few representative studies. Even before this has been studied by computer simulations, by experiments. We had done measurements long back in 2008. But before 2008, even during 1991, 92, 93, you could see in the literature that people were looking at compressibilities, dynamic light scattering measurements, X-ray scattering measurements, and several others. But all those studies were actually trying to understand the solution anomaly occurring at low alcohol mole fractions. And these low alcohol mole fractions, meaning water-rich media, where in the viscosity are being confined here, something like from 60% water to 100% water, where viscosity of the medium is decreasing as a function of alcohol, water mole fraction. However, in the azeotrope, particularly the ethanol water azeotrope, we are essentially in this regime, exactly opposite. This is the simulated and experimental data for viscosity for ethanol water systems. This is at 298 K, this is at 323 K, and this is at 351 K, is our simulations, and some data are available experimentally at two ends, pure systems. There are no data available, experimental data available for other mole fractions. However, they are kind of giving us confidence, some kind of confidence that we are probably predicting in simulations the right trend. Notice here that non-monotonicity at all temperatures. Well, sir.
And I asked this question in chat also, but I think better ask, everybody should ask in the middle of the talk also.
Yes, sir.
More informal. How common is this across alcohol, normal alcohol and water? There's only one, ethanol, right?
Right. So this thing is common, this non-monotonicity of viscosity.
No, I'm saying azeotrope. The non-monotonicity viscosity is okay. That is, I think one understands. But what about the
azeotrope formation?
Yeah.
Yes. No, ethanol water forms water, but methanol doesn't. Propanol does not. Butanol doesn't. Butanol does. So that is the thing that we'll be talking in the next few slides.
So ethanol does and
2-butanol does.
2-butanol does.
But not tertiary butanol. That famous systems that you studied, we studied that butanol water systems. So much of anomaly in the low mole fraction regime, alcohol mole fraction regime. That system doesn't form azeotrope.
Interesting. Yeah. Okay, go ahead. Yeah.
So again, then putting you back to the azeotrope formation and non-ideality, I show you again this overhead or transparency. I bring you to Raoult's law. As I said, that non-ideality of solution is a necessary condition to form azeotrope, but not sufficient. That means that if you have non-ideality, that's not an automatic guarantee for formation of azeotrope. And obviously, examples at your hand, methanol and propanol. There's two alcohols on the either side of the ethanol. Doesn't form azeotrope with water, but ethanol does. Question is, why? So definitely the question that you would be asking a physical chemist, that what exactly selects azeotropic pair? Because this formation of azeotrope, this phenomenon is solely driven by liquid phase mixture thermodynamics. And this liquid phase mixture thermodynamics is intimately connected to a specific relationship between component free energies. And these component free energies and all these things are all encapsulated in configurational integral. That means you need a particular orientation of the solute particle, which is in low concentration in the case of ethanol water, it is the water, and there should be specific orientation as we approach the azeotropic condition. And if that happens, then one expects transition in relative arrangement pattern as the azeotropic condition. That means you are expecting something, a change, a transition in the structure, if you are following the right variable. Another interesting thing is this, that azeotrope can form even when the vapor phase is ideal gas, because the azeotropic condition is that the partial pressure in the liquid phase should be equal to the partial pressure in the gas phase at the azeotropic temperature. So the entropy of mixing itself, even when your enthalpy is zero, interaction is zero for ideal gas, this entropy of mixing actually gives you the driving force for the formation of azeotrope, even when the vapor phase is ideal gas. So now, as I say, that the big question is what selects azeotropic pairs or components? Why methanol doesn't, while ethanol does? What dictates the azeotropic condition? How do I know whether there is any way to a priori expect or predict that this would be the composition and temperature for this pair to form azeotrope? And the question is, what exactly happens at the dynamical level that leads to the component to boil together? That means leaving the surface, both the species, hand in hand. If that happens, can we get a signature of it? And immediately, as a student of physical chemistry, we by now understand that formation of azeotrope is somewhat unique, particularly the temperature and composition. And we have already come across several such unique composition and temperatures, particular temperatures, when you dealt with colligative properties, upper and lower critical solution temperatures of binary mixtures, and also very recently it has come across to the physical chemists, eutectic systems, eutectic temperatures, whether they are sir.
But you know, it should be the chemical potential. No, partial pressure is a
no, sir. Chemical potential is fine, and that is to do with colligative properties. But for the formation of azeotrope, the chemical potential, even if it is impacted, if the partial vapor pressure is not impacted, then the
mu equal to mu naught plus RTLNP.
Right.
So if pressure is the same, that means chemical.
Right, but if your solute is non-volatile, then although it is impacting the chemical potential of the host, it is not influencing the vapor pressure because it is non-volatile. And on this ground itself, the colligative properties separated from the azeotrope formation process. This is a differentiation. Okay, so these three I'll just explain to you very briefly. And you know, when we as Professor Bagchi has already pointed out that how colligative properties vis-a-vis chemical potential relates to the formation of azeotrope, and if for colligative properties, by definition, it is to do with non-volatile solutes at very low concentration, which leads to depression of freezing points and elevation of boiling points. However, if they're non-volatile, it doesn't have any influence on the solvent temperature. And this itself excludes colligative properties being at the origin or have any connection to the azeotrope formation. And as I said, uniqueness, even for neat systems, this is for water, we know this critical point, this triple point, this boiling points, all are unique. And one can use the Gibbs phase rule, mostly in the case, if I specify the boiling point, then we are talking about normal boiling point.
But your component is 2.
Component is 2. Component is 2.
Yeah, but you have C minus P plus 1, you have Y, you have 1. This is the ordinary one.
This is
one component.
This one is degrees of freedom. So if I said normal boiling point, inherently I'm saying my 1 degrees of freedom I have already taken away. That is the 1 atmospheric pressure.
Yeah. C minus P plus 2. You have taken out 1.
Right.
Still 2. C is still 2.
C is component wise, it's neat water. H2O. Phase is 2. Phase is 2. No, sir, it is neat system now. It is neat system now in this transparency. It's neat system now. Okay. So phase is 2, component is 1, and that is giving you 0. And that means at the triple point, or degrees of freedom, that means number of intensive variables that can be altered without disturbing the equilibrium over here, phase equilibrium, is 0. That means once you fix the pressure for the triple point, the temperature is also fixed. This is the uniqueness. If we go for the binary systems, upper critical solution temperature, lower, and also systems which has both upper and lower critical solution temperatures, particularly for upper critical solution temperatures, you can increase the temperature and take it to higher temperature to find out whether there is any temperature, any composition exists where the vapor pressure at the liquid phase and the vapor phase equalizes, and that doesn't happen. So azeotrope formation has also nothing to do with this upper critical solution temperatures of binary mixtures. Some standard examples of upper critical systems with upper critical solution nitrobenzene, hexane, and then this is for nicotine and water, very interesting system, both has upper and lower critical solution temperatures. So we have seen this. Now for the debutectics, we know this is a unique point C, and if you same way, if you use the reduced Gibbs phase rule and you find out that point C, which is the eutectic point, you will find out that the degrees of freedom is actually 0. So all these things are unique, but for different reasons. Same thing we would see for phase diagram connected to formation of azeotrope. This is for high boiling azeotrope, meaning for those systems, binary mixtures, which has negative deviation from the law, Raoult's law, for example, HCl water. And you see here, it is the same liquid phase vapor pressure and the vapor phase partial pressure becomes the same. And you can see here the component now behaves like a unique component. Although they are different, but they are behaving at this point just like one pseudo complex. So I put it as 1. And you see here this degrees of freedom becomes 0. The same thing for this. So these are all having an uniqueness that could be understood from Gibbs phase rule. But the underlying reasons for each of these systems are different. What we found out, if we go to our experiments, we did ethanol water, and what we saw initially, this study actually started from our measurements. First measurements that we did is the dynamic fluorescence anisotrope measurements, where we took a solute like this, which has a fluorescence after irradiation of appropriate laser pulse. And then we were seeing how this molecule is rotating inside this mixture as we change the composition of this solvent at a temperature close to or at azeotropic temperature. And then we did also temperature dependent measurements. So we did several sets of measurements. In one case, kept the temperature at 351 and changed the composition. In another set, we did the reverse. We changed temperature at a sitting at composition. And what we found out, the uniqueness is here. This is what we show. The rotation tau is the average rotation time of this probe, which is actually found by integrating the area under the curve once I normalize these things to 1. So that we are seeing, and this is the decay of time-resolved anisotropy, and you see at different compositions. 4.5 is the azeotropic, and we are sitting at 351. And what we see here after doing several number of measurements, which gives you the error bar over here, and we see here there is some kink, and this kink is real. It's not like the error bar from measurements. It's not the random error. So what we saw here is there is something, and the diffusion is becoming slower, rotational diffusion. And when you did it for the entire composition, you can see here that it is going down to something like this, which is going to meet the water, normal water kind of thing. And we wanted to look at that whether there is any structural uniqueness in this composition, whether the system is heterogeneous, whether the small amount of water is being surrounded by waters through formation of clusters of different sizes. If that is the case, then we should be able to find out the signature of it through spectral measurements. It will give me information if we do appropriate photo selection. That means that I have an absorption and I pick up the population at different energies and let them relax with the solute being dissolved by those solvent configurations. And if they are slow in the sense that is slow in comparison to the elution time versus the fluorescence light time, I would see the fluorescence emission going at a different positions. And if I appropriately analyze them, and we see here that the emission shift that is happening as a function of composition, we see that at this particular composition, which is the azeotrope composition, shows a signature of the system being the most heterogeneous. So these measurements then fuel us, further thinking that what could be the solution structure and what is happening to the transports, particularly the center of mass transport, as well as the rotational motion of the particles itself. That means not the solute, but the composed components, the water, as well as ethanol. So when you put them in solutions and look for the formation of clusters. These co-clusters means that water molecules being surrounded by ethanol molecules, and this is composition dependence. And you can see here, it's a normalized plot, that as we decrease the water concentration, the system heterogeneity increases. That means the various size of clusters they are appearing. Although the relative populations are much less, but still it spreads over the entire broad region of size. This tells me that our kind of explains what we saw in steady state absorption measurements, that at this low mole fraction, which are loosely called below 10% water content, is a near azeotropic mixture. And we see a real signature even in simulations. That is the thing. When we plotted the relative fluctuations of the interaction energies, what we saw, interestingly, that water-water interaction energies are
Ranjit, can I
showing.
ask you a question?
Sure, Arnav, sure.
Okay, so the last slide, I think I need to understand that. So did you do the experiments at normal temperature, room temperature?
And yes.
Did you see this kind of
No.
Okay.
That is
And
not
the second thing is that in the current slide, go to the next slide. So here, the co-cluster size plot.
right.
So let's say 4.5%, which is an
Right. Azeotrope, and we are sitting at azeotrope temperature. Yeah.
There you see a variation in the cluster size. I would have expected almost an uniform distribution of sizes at that, if I think that they are forming azeotrope or clusters of some size together. So this kind of goes against my intuition.
If you had the uniform cluster size in spectroscopy, you would have seen that signature. Okay, the heterogeneity, that is essentially the signature of heterogeneous environments.
Okay.
Okay. So if you had, let's say, the cluster size is only 5 ethanol molecules or 6 ethanol molecules surrounding each water. So that is essentially homogeneous distribution of the cluster size. And you would have seen that in the spectroscopy.
Okay, this is very interesting. Okay, continue, please.
Okay.
Yeah.
Okay, but then this relative fluctuation is coming around 4.5 or something like that, which is very encouraging. But here you see, if you follow the concentration, this is pretty mundane, pretty regular. There is nothing unique in the cluster size distribution. It's fine that it is explaining our spectroscopic data, but there is nothing unique. If you go to the number of hydrogen bonds per water molecules or ethanol, and that kind of thing, that is also is pretty regular. It is telling you that just the concentration dependence. There is nothing unique. Hydrogen bonding distribution or the tetrahedral angles or the order parameters, they are all kind of telling you that it's a regular dependence. This means that if there is anything structural uniqueness, we have failed, miserably failed in detecting that. However, when we looked at the enthalpy of mixing, we wanted to look at whether it's something happening at the free energy change due to mixing. And what we found out that when this is nice non-monotonic dependence, which you even expect for ideal thing, but as you switch on the interactions, both in the enthalpy and in the entropy, this peak will shift in this way or that way. But here, this is not coming down and approaching certain value. You see here leveling off. So it's a huge change in the slope. We actually looked at whether this is coming from system size dependence or interaction potentials. Our study so far tells that this is, yes, two-phase 2PT method was used to look at the entropy. Well, Sarika, yes.
Yeah, sorry. So when you talk about change in enthalpy of mixing, what do you mean by change in, means change from what to what?
Pure to mixture. Two components to mixture. And then their mole fraction weighted average minus what we see after mixing.
Okay, yeah. So independent. So basically, okay, fine. This is only enthalpy, not okay, fine. Yeah.
Entropy also we did, because entropy contribution is a factor of 20 less than what we show here, the scale. In this case, so even if I add that, the delta G mix doesn't give you a better, finer picture, or doesn't provide any super resolution to it.
Okay. Yeah, sure. Thanks.
Okay. Now go to next. Change. This is not changing. Why? Let me click. Okay, so now, of course, we wanted to look at radial distribution function, and as I said, that we did not see.
But you, sorry, again, you did not say why the slope became flat. Do you understand why it became flat? Why the enthalpy of?
We are trying to accumulate results first.
Okay, okay, fine.
And it has to have some connection somewhere to the structure. Yes. But this kind of conventional processes to find out structure is not giving us anything very interesting or particular. That's what I'm telling you, describing you, that G of R and all those things which we usually look at is failing to produce or give us anything. So all what we are seeing is simple dilution effects. All kinds of water, ethanol, ethanol, water composition at the azeotrope, at the temperature that we are varying. There is nothing unique, this kind of thing that we are seeing. But then things are very different when we look at the dynamics. What we are doing here in this plot, you see that we are plotting the center of mass diffusion coefficients. And we are plotting the ratio of dW, that is water diffusion coefficient, by dE, and plotting in a log-log plot just to find out 0, 0, 0. So this means here is that diffusion coefficient of water is becoming equal to the diffusion coefficient of ethanol. That you expect, that at this concentration, which is 0, that means the plot is percentage of water normalized by 4.5%. That means this is the azeotropic composition. So at this azeotropic composition, the diffusion coefficients of the components become equal. This equalization of diffusion coefficients of the components we thought would be a signature, a dynamical signature. And this must be an effect. This cannot be the cause of formation of azeotrope. So that is something which is kind of, we are trying to find out what is the cause. And this is intriguing. Why intriguing? Before telling you, let me show you the particle diffusion coefficients, individual particle diffusion coefficient is simulated and found out the distributions. And you see, very interestingly, at the 4.58% or 351, they are kind of merging on each other. They are approaching, and then at 4.5%. You further lower down the water content, and they are differentiated, separating from themselves. So we thought this could be a very good signature, a mixed dynamical signature of formation azeotrope. And this is intriguing because in the next slide, I'll show you that we are in this area, right? Low water content. The viscosity is increasing. But what we are seeing that diffusion coefficient, all these things, what it's doing, you see here, that water diffusion coefficient in this plot, they are going up. Very interesting. Ethanol is going down, but water is going up. So water is behaving in a very anomalous way. And you can see here in this plot that we are sitting at the azeotropic composition, changing the temperature. And when temperature becomes azeotropic temperature, you see again that equalization of component diffusion coefficients. Very intriguing. I connected this to the viscosity of the medium. Then we thought that we should look at the second rank reorientation time, because that second rank reorientation time you can probe by 2D IR measurements, and people have done that. And what we saw here, when we did that, we found out that they are policing this distribution, rotation time of water. The distribution is actually overlapping perfectly with each other, but at a mole fraction different from the mole fraction at which center of mass diffusion coefficients distribution masked, which is 10 weight percent. And this is understandable, as we know that the rotational friction or rotational diffusion coefficient is averaged out in a manner somewhat different from the averaging out of the transitional diffusion coefficients. So, but here one thing is interesting, that the diffusion coefficient is actually crossing each other. And you see tau2, which is inverse of diffusion coefficient, in this range, that viscosity is increasing, but regeneration time is decreasing. So this decoupling. And this decoupling has to do with the local structure. Something must be happening at the hydrogen bond, local hydrogen bond level, and their lifetimes, because these time scales are pretty small. And if you look at the hydrogen bond lifetime at that elevated temperature, they must be very comparable or even lower than this. So there is a competition between the rotation time and the hydrogen bond lifetime. And first time regeneration time we also calculated, because this can be probed by us in our laboratory itself through dielectric glaciation measurements. And what we saw here, that we did not see any overlap of these distributions, and they did not cross at any level, but that magical thing, the dependence of water concentration, still continues for water. This means that the rotational diffusion is increasing even when the viscosity is increasing. So this is quite interesting. Then we thought that, okay, this is simulations, we're using potentials, classical potentials. Let's see what the measurement does. Can we see something? Same thing in the experiment itself. And this is a comparison between experiments and simulations. These things, you see, this is 300 Kelvin, this is 351 Kelvin. So these on your left panels all are at room temperature data, and the right panel is 351, that's azeotropic temperature. And this is very interesting. This is time constant. This time constant is also decreasing as we increase the water content. What we are exactly thinking of, why it is happening, and this is pretty general, even at 351, although the numbers are faster, smaller, time constant, but the composition dependence is similar, very similar. So why? Question is why? Now, the thing is this, that whatever we have seen, whether it is any general, that the equalization of the component diffusion coefficients, can we take another mixture, known mixture that forms azeotrope, and also follow the same thing, calculate the diffusion coefficient distribution and other things? Can we see that equalization of the diffusion coefficients? And exactly, this is for 2-butanol water azeotrope. The azeotropic temperature is 361 K. And what we see here, that at 32%, which is the azeotropic composition, we see the equalization of the distribution itself. So this is kind of giving us a clue, the initial clue, that probably these are the unique dynamical signature. Then the opposite test should be done, that pick up a system, maybe propanol water or methanol water, and follow their transport coefficients and see whether you see or you don't see. If you don't see, then what we are getting at would be bolstered. So what we saw, this is very initial results. My collaborator Pradeep, who is doing the simulations, he sent me just 2 days back, and what we see here, they're pretty close, but not equal. The temperature that we have chosen is 334 Kelvin, and the logic of choosing this temperature comes from the boiling temperature of methanol, which is at 337 K. Also, for ethanol water system, the ethanol water azeotrope forms at 351 K, which is a couple of degrees below the boiling point of ethanol. So we thought that, okay, take this system to the boiling, near to the boiling temperature of the alcohol and look at whether there is any equalization of component diffusion coefficients. And we don't see that. So is this pretty general? For that, we need to study propanol water system and many other systems to find out both. And then the conclusions comes is this, that this motion of the particles are strongly correlated, but we still do not know how to understand this, that the viscosity goes up, but the reorientation times or the diffusion time scales actually becomes faster. And how that correlates with the hydrogen bond lifetime of the systems, particularly structural hydrogen bond lifetime of the systems. With those questions, I would like to conclude this talk, and part of this has been published in this year. And my acknowledgement, I have already acknowledged Pradeep, and this result simulation was done by Shrestha at IISER Kolkata with Pradeep, and the experiments have been done at the SNBNCBS Center. Thank you. I'd like to take questions, comments, please. Thank you very much.
Thank you, Ranjit Da, for a fascinating lecture. And now the floor is open for discussion, questions, comments. Okay, so in the chat box, there is already a new question from Shravan, I think. So Shravan, if you want, you can ask it directly yourself, or I'll just read the question. How does the diffusion coefficient of water in alcohol water azeotropes vary with temperature changes? Is there a particular temperature range where diffusion is notably affected?
Well, for your question, the temperature range that we have looked at for ethanol water, we have seen the uniqueness that I have shown to you in the part. That happened only at that temperature. There is a dependence, there is a non-monotonicity, and the dependence is different for ethanol diffusion coefficient and water diffusion coefficients. But that uniqueness is only for that azeotropic temperature.
Okay.
You can see here the temperature dependence over here.
Okay, Suman, can I ask a question?
Yeah, sure.
So, Ranjit, so if you summarize the things that are getting affected, I can see that the diffusion coefficient gets affected and rotational relaxation time.
Right.
That also switches. Like I'm talking about ones that cross over.
Right.
Rotational relaxation time crossover. However, dielectric relaxation, there is no anomaly.
Of course, there is anomaly. You see here? DR time becomes faster, although viscosity increases. You see here?
Okay. So somehow the dynamical quantities get
more affected.
Faster. Becomes faster.
Right.
However, the diffusion coefficient, if you see with respect to this thing, is it getting slower or faster, or there is an anomaly? I know that there are matching.
Anomaly. You see the water diffusion coefficient, transitional diffusion coefficient, you see there. You see here? This is water, red. You see what is happening?
Okay.
But
so now my question is that, so many of the dynamical quantities that you have shown, they have anomaly at the entropic composition. Okay.
Right.
At a temperature which is close to boiling point, right?
Azeotropic temperature.
Right. So two questions. One is that at a normal temperature, what is happening? What kind of dynamical quantities they have?
At normal temperature, our study so far has shown that it doesn't cross. It doesn't become equal.
Right.
Okay. But now you can say that, we have done a quick scan with the 10.1 mole fraction difference. But who knows, if I do it at 0.05 mole fraction, they would come pretty close or not. We do not know.
And the second thing is that the simulation result is if you go to the cluster size, this thing, radiation, then there I don't see any anomaly there.
No, there is no anomaly. That is the point.
So that means it is that all these things pointing towards a dynamical,
Yeah,
not a
right. But those anomalous dynamics that we are seeing must be resulting from some underlying structure. What is it?
Yeah, okay. So that is still unknown. That's what.
And these are the questions that are being brought for the first time in azeotrope.
And in
you can see the
enthalpy calculation result,
right.
From simulation, you can always figure out why it is not changing.
Right.
Because it's a simulation result. So
right. We can We can see that.
You can probe it that why why they're remaining.
Right.
Yeah. So another thing yes I would like to point out is that although many of the experiment and simulations are matching, but what we have, because we are working, what we have found out that these force fields do not capture properly the temperature dependence effect. So for example, boiling point, right boiling point is very difficult to get.
Yes, I recognize your question.
So we don't know the based on the force field of the present system. What is the actual temperature at which?
This is a concern, and for this we have picked up potential which has successfully reproduced within 10% or 5% the azeotropic temperature and composition for systems which involve either water or ethanol. Okay, and these potentials are TRAP, TRAPPE, transferable potentials for phase equilibrium studies. Okay, so when people use that potential for neat systems, they found out, they reproduced the boiling point within 1% of the experiment. Not only that, for example, when they reproduce the phase diagram of ethanol benzene, they got it. They got it pretty close. You know that.
I know that.
Ranjit,
sir.
I do not think force field issue is the major issue here.
Okay.
The major issue, probably we did it, but we never, with I think Rikia or Milan we did, but we never went to that. Though I was curious, but we never did that. One thing that one should do is study the second order properties, because first order is clearly not doing it.
Right.
So that means you have to look into the specific heat and maybe isothermal compressibility.
Right.
And because it will be exceedingly difficult to get the structural signatures.
Right.
So we did it water TMS or water ethanol. There's never really any very clear, because things are very transient. So, and then there's cross correlation between different, that means all the second order properties.
Right.
And then also, if you look into it, exceedingly difficult and taxing. When GR fails, then one can look into G3. Is there any signature of water? See, you have a very small degree of water. So water have to consider multi-particle correlations with ethanol.
Right.
Is there anything? See, molecular picture would be, you have that guys in liquid, you translate them to gas phase.
Right.
And so the same kind of structure holds, right?
Right.
And that means certain many particle level or multi-particle level, you probably will have some signature. I am forgetting, but in one of the studies in 1980s with A.D.J. Hammett and Stuart Rice, they looked into many particle correlations and they found a lot of very beautiful.
So we should try to look at many particle correlations, right? That's what you are.
G3 at least, G3. G3, I see, we have to consider that you have only 5% water. And then these waters are entropically should be dispersed.
Right.
But they will be surrounded by then solvation. Then that part you can see with
Right.
solvation. So they are solvated by ethanol molecules.
Right.
Now, so they are hydrogen bonding. Now, why that arrangement is so stable?
Right.
So I think you might be able to get that. And see, also, I think one factor will play a very important role is the hydrophobicity of the ethyl groups.
Right, right. There must be a subtle balance, which is actually dictating the pair choice, choosing the right pair.
Yeah, exactly. So if you look into this molecular arrangement of ethanol around the water, look in the liquid and look in the gas. And they are very interesting because they are going as same,
Right.
So the structural, a many particle level structure, 3-4 particle level structure.
Right.
With the hydrophobicity and see, when you look at for example, supercritical, you have done that paper. You have properties of water solution, remember? And there are very interesting things that we found that is the ultra-fast solution.
Right.
But at the same time, the mechanism is very
different.
Supercritical is same as subcritical.
Right.
But completely different mechanism.
Right.
So it might be something like that. So my recommendation: look at the response functions, second order properties. Look at the multi-particle
correlations,
G3 and G4, and look at, and what would be really very nice if someone is there to make the movies. Water. How is ethanol oriented at water? When you read that in water DMSO with that Sushmita did, 15% the water DMSO we found a very interesting structure. So look at the structure at many particle level. That would be probably very
informative.
Will tell you a lot of things. Clearly, it's I refuse to believe it will be too subtle. It is such a phenomenon for 200 years, right?
Right.
300 quarters. And we have not been able to explain.
Right.
And you have a shot at that. And you should go at it. And that way, as Vinod Singh was so excited because I think, Vinod is here or no? Okay. But, Vinod really likes neat alcohol. So, I don't think he goes to 95%. But still, he was obviously very interested. Okay, I think very good work.
And can I?
Sure. Sorry, sure.
No, because probably my question is quite stupid, but still I thought. So you did look at the hydrogen bond lifetimes also, right?
Some of them, not fully. And we found out the hydrogen bond lifetimes are extremely shortened at this condition that you expect because of the temperature, right? So I can show you a distribution if I have. Let me just find out if I have. You see it here. This is that we did this paper and supporting information that we provided.
So I'm lost now. Where is 1%? 1 weight percent 4.50. No, so where? So which is your azeotropic
351 4.58%.
That's
the green
one.
The green.
The green one.
Right.
And, yeah. So there is no extra stability. No, anyway, you are finding a diffusion going in the opposite.
Right. So I was thinking first, since we are data collection doing at the beginning, that if I plot the diffusion coefficient of continuous and structural hydrogen bond lifetime, what do we see? Is there any correlation? There must be some correlation somewhere. So first find that out, and then try to use that to look back at the structure, as Professor Bachi is saying, that how ethanol is reoriented and water is oriented, and all those things.
No, it's okay. Yeah. Anyway, I'll talk to you later again. Very,
Sure.
very interesting thing. And the fact that you got diffusion always the same in that.
At that mole fraction.
Yeah.
Right.
What is,
at that condition. Yeah.
and that is only at that.
No, that will happen anyway, you understand, because both these species is leaving the surface at the same time. Because azeotrope composition, if you keep boiling, it will not change the composition.
Right.
So both of them will leave at the same rate, hand in hand.
There must be some, many particle effects here. That's all.
Right, right.
That is the reason it has not been explained for so many years.
Right, right. There is no, yeah, right, you're right. Yeah, very subtle. So we have to find out multi-particle thing.
Yeah. First, look at the picture with the movies.
Right. Right.
You must look into movies first.
Okay.
And then you will see that the ethyl groups are packed together and one water molecule is inside, and but it is somehow stabilized by hydrogen bond. See, I found one thing. I'm writing a paper on that the loser Chandler and other people say, okay, water DMS hydrogen bond is twice as strong as water hydrogen bond. Which is stupid, because DMSO oxygen is negative charge about -0.4. Water is -0.8, right? So it cannot be strong, but it is effectively strong through hydrogen bond lifetime. The reason is that the methyl groups are forming a cage.
Right.
The hydrophobicity of the methyl groups are forming a cage, and that is holding the hydrogen.
Right.
So I should write the hydrogen bond strain, the hydrogen bond effective potential be effective as water DMS hydrogen bond there plus an effective.
Right.
So if you think of a spring constant, this will be spring constant will become that means much steeper.
Much steeper potential, yeah.
Exactly.
Okay.
I think this ethyl groups, the hydrophobicity of C2H5 must be very interesting. That will be a lot of fun looking at the movies,
So kind of telling that the curvature of the potential that is dictating.
One water molecule surrounded by 5-6 ethyl groups would be a lot of fun. That those C2H5s are all hydrophobic. They're
right.
But their hydrophobicity is not as strong as that would be when there is more water. You see, hydrophobicity is a term when there's a lot of water.
Right.
So as we increase the ethanol concentration, two things are happening.
Right.
One is the effective hydrophobic interaction between ethyl groups is decreasing.
Right.
But the number of ethyl
interaction is increasing. Right.
So I think the secret really lies in the hydrophobicity and the role of water caged in such a nice way.
Definitely.
Which transcends to gas phase.
Right.
So look at this movie. Movie would really help you.
Yeah.
Ranjit, can I ask you a question?
Sure.
So can you go to that slide where you showed that red edge effect?
Okay.
Yeah, this. So you're saying the heterogeneity is causing these effects, sir?
Yes, this is a signature of heterogeneity.
So these are experimental data in solutions, I believe.
Right.
So
with a probe over N343. Yeah.
Will not get averaged out?
No, because you are photo-selecting different populations, and they have equilibration time different from the lifetime. Okay, then only you see in solution phase heterogeneity. There must be a competition established. It is coming from Kasha rule in fluorescence, and Kasha rule demands that before the fluorescence arrives at your detector, the different solvent configuration must be equilibrated fast enough.
Yes.
As if then your fluorescence emission is occurring from an average solvent configuration. But if there is a competition, then you see the fluorescence emission is occurring at different energies because of the excitation of photo-selected different solvent solute ensembles.
Okay, because you are looking at low temperature, it's 351 Kelvin.
It's not low.
It's 351.
That is very interesting. 351 Kelvin.
351 Kelvin.
So it's about 78.
It's yeah, it's higher, high temperature.
Yeah,
So
that's why it's so interesting.
So how is
There must be stable cluster formation, and that's what we are showing in simulations.
but
That,
do you see
yeah.
that in anisotrope measurements?
What?
Do you see
And
that
of course, anisotropy you see here, the lifetime, the diffusion time, the rotation diffusion time is showing anomalous composition dependence, and the peak is occurring at a mole fraction or 8% of water, exactly at the azeotropic composition.
So there is at that composition you have cluster formation.
Right. The temperature we are sitting at azeotropic temperature. So these are the things, the experimental findings that inspired us to look at simulations. What is happening at the microscopic level?
Maybe that is breaking down at high, like higher water percentage.
It's not. Could be something is happening. Definitely, the friction is less here at the higher mole fraction. So definitely at the structural level, something happens, and that we know for alcohol water mixtures. You know, if you add water drop by drop in ethanol or alcohol drop by drop in water, the structure changes. First, the water try to retain its three-dimensional structure by restricting its entropy, configuration entropy, and then finally it breaks down. It cannot host anymore. All those things are known for low alcohol mole fraction, and they are actually at the heart of the anomalous mole fraction dependence. However, we are now looking at the other end, the rich alcohol concentration, that solution. So it has to be the interplay between the hydrophobicity and the hydrogen bonding. Yeah.
So there's that composition like sweet composition, sweet spot.
Right. And it is different, right?
Thank you.
Thank you.
Ranjit,
Yes.
This is Ananya. I have a question about your anomalous behavior of diffusion constant, which you are showing in the plot, maybe in the next slide. Yes. So when you have such a low water concentration, do you observe any percolation behavior?
We did not look at that, you know. We did not look at that. We should see that, because these are very first studies, initial set of results. We must look at.
So as Professor Bagchi was telling, that the there are many other systems where you see very strong dynamical anomaly, whereas the structural signatures are not so prominent.
We saw it.
But
we saw it.
Similar things.
For example, here,
observed. Yeah.
2-butanol water system. Representative results shows this is the azeotropic composition, and this is the temperature, azeotropic temperature. So sitting at azeotropic temperature, we're doing composition variation, and you see here.
Right.
But pick up a system which doesn't form azeotrope experimentally. For example, methanol water, and it comes pretty close, but it is not becoming equal. Yeah. Okay, but this kind of thing should be done more and more and find out.
Yeah. I was thinking actually in many of these systems, like the Sarika's nice work on this PRL, where he showed that this higher order G3 or S entropy, plus higher level entropies. This is, I think we must now look into this multi-particle things. Multi-particle, I'm saying not 3 even. In this case, you need 5-6 particles. That's why it's about time that we physical chemistry, because we have too long G2, G2. You know that there's nothing in G2. Many of these things are in higher level.
Right.
Is there any other question or comment from anybody? If not, maybe then we can stop here. So let me, on behalf of all the other coordinators of SMCB seminar series, let me thank first of all the speaker, Professor Ranjit Biswas, for very interesting work and also the subsequent discussion. And also
thank you,
Bagchi, for chairing the session and of course mentoring the whole seminar series. So we thank all of you for being here with us. So that's all for today. And
Thank you.
Yeah.
Shuman,
Yeah,
the
yes.
the book has appeared now. The non-equilibrium statement book.
Yeah, so we have a good news that the book on non-equilibrium statistical mechanics by Professor Biman Bagchi is out now. So
Okay.
All
Yeah,
of you buy 2 copies. It is cheaper.
Yeah, I have already put the requisition in our library, so hopefully we'll get a copy.
You have
Also, I'll buy a personal copy for
like Ranjit did last time.
Yeah.
Yeah, I bought all of your copies, sir. All of your books, 3 or 4 books I have bought, and also the story books also.
I remember.
I'm reading also, not buying, reading also and asking students to read.
Okay, I signed them. That I remember. No, it is not. I'm saying for myself, but publishers are in really bad shape.
Right.
They are very poor. They are almost going out of business now. They have stopped publishing. So in our lifetime, we'll see that hardbound books are going out. And in front of my table, I have this one. This book. If you like this, but I made fun of Amalinda complaining, but this is the book I just in front of me have now. So, Suman, have you read Srinath Datta?
Yes, I mean a few, not all. I mean I know a few like
Shashwati is the most famous poem by Chudindranath Datta.
Yeah. We are thinking of having this literary forum of scientists, LFS. If we can do that, that will be a lot of fun. We'll make Amalinda the president. Okay, then. I'll
Okay, sir.
Yeah.
Thanks
Okay,
a
sir.
lot. Thank you for great talk.
Okay, sir. Thank you. Thank you.
Thank you, everybody.
Yeah,
We
bye-bye.
will announce the next lecture in due course and
Okay.
announce in our mailing list. Yeah.
Okay.
Thank
Thank
you.
you. Thank you.
Bye.
Bye-bye.